So my name is Alexander Krizhanovsky, and let me start from what this presentation is about. The first thing is that we develop TempestFW, which is a hybrid of HTTP accelerator and firewall. It's embedded into the Linux TCP/IP stack, so it works in different interrupt contexts. And the main purpose of the project is to process large traffic and protect against volumetric DDoS attacks. So it means that we need to process a lot of HTTP requests, and also since the project works in Linux TCP/IP stack, we have a near real-time requirements to all data structures used in the project. Since it's HTTP accelerator, it means that it caches web content, and the core data structures of the project is web cache, which is typically data structure indexed by URL and host, so this large string key and some data, usually quite large data like modern images, web pages, or whatever. From the other side, we had a couple of requests from our clients about investigation of performance issues with their current data structure. The first request was from MariaDB. It's expressed in MariaDB 2630 development issue, and the problem was about split order at least and the significant performance degradation. We'll talk about this data structure later on the presentation. The second request was from one of the PostgreSQL developers about their internal data structures used for transaction handling, not the main database index data structure, but helping data structures to handle transaction descriptors. We also concerned about tail latency. Recently we had another request from our client about the huge tail latency in the CDN, and the thing about tail latency is that it's always about big numbers and very busy machines. For example, if we consider a very large CDN, having a lot of CDN nodes and hosting a lot of web resources and processing requests from a lot of clients. The first thing is that you might think that, for example, if you hit only one slow request or from 10,000 requests, it's not a big deal. However, if you scale, then a lot of users may have see a very bad web resource. For example, you imagine that your header image on your website header just cannot be loaded. So this is a big issue for any website owner. The second thing about tail latency is that it's always happen on a busy machine. For example, if you do make a benchmark of your program, and some of the tasks require sub-second delays, for example, several microseconds. Then when you go to production and you experience significant loads, then your operating system goes under stress, and the CPU scheduler can provide up to 1 second scheduling delay. This is what we observed on in the blog post, is that Linux operating system scheduler provided 1 second delay to schedule one process to another. So if your if your main process requires some relatively long time slice to finish some operation, for example, rehashing of your main hash table, it can be scheduled several times, and each time it can wait for up to 1 second in a run queue. So we can get a huge tail latency. So in our case, we work with data structures database. So as I mentioned before, Tempesta FW catches web content in a data structure. So we have several contexts for our data structure. So the most performance crucial path is lookups and inserts. So since this is about web cache, so we usually expect more lookups than inserts. Deletions happen, but quite rarely, usually on data evictions. So deletions can be relatively slow. We need to say several words about log-free and wait-free systems. Typically, we build log-free data structures. They're more straightforward, and basically difference between log-free and wait-free is that in log-free, any given CPU or thread can starve for some time, but the whole system makes progress. In wait-free is a more strict requirement which guarantees system-wide throughput, that all the threads do progress. This live locking problem can happen in log-free systems when, for example, several threads constantly pulls resources and cannot make any progress. So in log-free design, we have to keep in mind live locking. In all the data structures which we explore today, deletion is a real problem. The main thing about deletions is memory reclamation. From one of the sides, deletion is quite similar to insertion. So we just make some changes to internal index nodes in the data structures, and typically we can use the same techniques as we use for insertion. However, the biggest problem is that at some point of time, the index data node or referenced data node can be freed by the system, and we have to make sure that there are no observers currently working with the data or index node, and this makes the data structures removal very sophisticated. The second thing is about memory fragmentation. This is most about memory allocators, and basically when we talk about very fast and very scalable data structures, we need to talk about memory allocators. So we don't need very fast and very scalable insert in a tree or hash table itself if we have very slow memory allocator. So typically when we develop very fast and scalable log-free data structures, we have to work on scalable and very fast memory allocator. And once we develop efficient and scalable memory allocator, we have to take care of memory fragmentation and what to do with freed memory chunks. There are several techniques available for data removal from arbitrary data structures, for example, hazard pointers or read copy updates. And one of the popular way to cope with data removals is dummy nodes used in split order trees, several queue implementations, and so on. Our current data structures, which we will consider in this talk, is used in TempestDB, which is a part of Tempest FW. As I mentioned before, this kernel space, so near real-time requirements, and we develop it in that way. It can be accessed from many CPUs, including large NUMA system. Also, this in-memory database, so the web cache is in memory. It's hosted mostly in the RAM. However, the web cache must be persistent. We do need to write all the collected data to disk on shutdown and warm up the cache on system start. So we one of this particular requirements makes us stuck with data offsets in a flat address space instead of raw C or C++ pointers. So the persistency at the moment works as a simple write or mapped areas. One more thing about web content is that it requires duplicate key entries. For example, when your cache must contain current copy of the data along with a stale response. And also, if you use a hash table, collisions are possible. One thing about the database is that it must support multiple indexes. For example, we have the main index for URL by URL key, and also we may need designated index for vary. So this is like primary and secondary indexes for real databases. So a few words about the stored data. The most crucial case is surely web cache. So this is about the long string keys, URLs. URLs are some kind of problematic keys because most of the URLs have common prefix. Also, they have very long strings, and if we use plain Patricia tree, then we have a lot of collisions in the intermediary nodes. If we use hash table, then collisions might happen. Besides the web cache, we also target the data structure to store small records like client accounts, session cookies, and so on. The main thing about the different data records is that from the first from the one hand, we have large data stored in the database. The large data have very different lengths. For example, some of your images can be very small, some of them can be up to several kilobytes. From the other side, the other records like a client's account, session cookies, filter rules, and so on are actually just fixed size records and typically small records. So we'll consider mostly these two different types of records. So let's compare the trees and hash tables for these types of words. Trie, this Patricia tree or Radix tree, that's the same name, provides ordering. So we can make range queries on the tree, for example, to traverse from one URL in lexicographical order to another. With hash tables, we don't have any ordering, so in C++ we have them as unordered maps. So we have no orders. Hash tables provide very fast queries for when you need to look up or insert a particular key. But they typically trees and hash tables both need some reorganizing, like rebalancing for binary trees or busting for our hash tree, or hash tables need rehashing as they grow, or from the other side the collision chains can grow indefinitely. A few words about memory allocation. I mentioned this topic bit earlier, but now I want to reference a very good talk from CppCon 2019 about compression of the pointers. We use very similar techniques how to compress pointers to smaller offsets, and also about specific allocation tasks. The first one is that we need to care about spatial locality. So if we consider index data structure, for example, some tree and the data itself, when you start to issue the query, you first you need to run over your index, traverse through the nodes. And only after that, when you fully resolve your index, you go to the data. So with this mean, all the index nodes, and preferably in this sequence as you traverse them, should reside as in smaller piece of memory as possible on near pages or in a single page. From the other side, the data blocks can reside in completely different memory locality. So in this sense, generic memory locators don't provide you good spatial locality, since once you insert a new item, you allocate several index blocks. After that, you place some data, and after that you place again some index blocks. So data blocks and index nodes are intermixed in the memory. So generic memory allocators do not provide a good spatial locality. In our case, for our H-trie, we split our flat mapped memory area into extents by 2 megabytes of size, which is equal to one huge system huge page. And one of the huge page is used solely for index nodes, and another huge page is used for data nodes, and we can intermix the pages. So if one of the page was allocated for index nodes, it's used only for index nodes solely. Let's have a look on binary tree. For example, if we consider to use std map as a read-black binary tree in our program, typically it's possible, and there is protocols to provide binary tree log-free access and insertion. However, that's not trivial, and basically it's very hard to implement binary tree, balanced binary tree in log-free manner. If we use with a binary tree in our programs, typically if we use std map, then we're bound to use huge log, while in best cases read-write log. For example, we in our benchmark we used read-write spin log, which is unfortunately there's no read-write spin logs in current standard, but we ported it in our benchmark from the Linux kernel. And if we compare them with a simple hash table written by hands, we ported this particular hash table from the Postgres SQL, and hash table with plain mutexes per bucket provides significant better performance on 75% lookups and 25% inserts. So binary trees protected with a global lock are completely not scalable. Hash tables in this sense are more scalable. They can be implemented with fine general locks. It's not so easy to do with standard STD unordered map, and typically you need to implement them by hands. However, hash tables require rehashing, and rehashing typically require global log and takes some time because data copying countries the control box is required. So this is a great impact into tail latency. In our case, we didn't want to. Of course, we need to do some data structure reorganization and something like rehashing, but we try to make it as small as possible and not global. So we do rehashing with small pieces of data. One of the interesting implementation is split ordered list. They were relatively widespread. For example, you can find them in the wild in Intel thread building blocks as a concurrent unordered map. It's blazingly fast implementation, and also you can find them in MariaDB transaction descriptors hash table. However, in MariaDB there was issue still open, is that when you populate a lot of data into the split ordered list. By the way, split ordered list is a representation of log-free concurrent hash table. So if you populate a lot of items into the hash table can grow to very big size, and the hash table uses dummy nodes for log-free mechanism. So once you delete all the nodes, live nodes, you have the hash table almost solely consisting of a lot of dummy nodes. And when you start to insert the new portion of data into the split ordered list, you face that you need to handle a lot of dummy nodes, and this causes significant performance degradation. This is a subject for this MDF. And also, this no miracle, Intel thread building blocks also do not have erasing log-free. So once you need to erase some element from split ordered list, you need to acquire a global log. You can only insert and look up in the data structure concurrently. Let's have a look on Radix Trie. We will take a deep look onto Radix Trie because our implementation is based on this data structure. One of the example is Judy arrays. We can say that there are some optimization of Radix Trie which provides very clever and several techniques to compress Radix Trie. So the Radix Trie is shown on the picture. If you use Radix keys, then typically you have nodes. In Julia arrays you have 256 items per each node. So, for example, if you have a 4-byte key, you have a radix tree of height 4, as on the picture. So each byte of the key resolves a particular level of the tree. This data structure is nice because it's fixed height, so you have a constant access time. This is pretty nice. Basically, you need only bit operations and pointer dereferencing to work with the data structure, so it's very easy to implement and very easy to make it log-free. However, the drawbacks of the data structure is that it's memory greedy. So if you have a lot of keys and the keys are uniformly distributed among the whole key space, then you start to lose a lot of memory for intermediary indexing nodes. So for example, each of the node which can address 256 keys use it only for one branch to resolve only one key. So Julia array uses compression to avoid such cases. Also, there's research which helps to compress the Trie. In this picture, in the data structure, we take care about other type of compression, not only when a single node is used for only one key, but also when a sequence of index nodes used to build a single path to an item. Consider unique URL with a unique character. So if you have a different URLs starting from after block slash, you have different characters in URL, and if you resolve a character by each node, you have a very long traversal paths in the Radix tree. So art proposes to compress the paths. Another technique used in our case is bursting trie. So let's consider what it is. So in a nutshell, bursting trie starts from a basic hash table. I will show the picture and code bit later, but now just a basic description of what it is. So we start from a hash table, very small one, and we keep buckets, and we keep fixed size collision chains, and once our collision chain grows too big and we consider it as inefficient and we have a different heuristics for inefficient, we burst the collision chain and insert additional hash table. So we have a 2-level Radix tree and split the collision chain into several buckets, and we can repeat the process. We'll discuss the performance issues and trade-offs of the bursting tree bit later. At the moment, let's say several words about x86-64 CPU caches and data model. In our case, we care about cache-conscious data structures, so the memory organization is very important for us. The first one is that the architecture works with 64 cache lines. This is a data unit, so when you access, for example, when you read just an integer from main memory, you actually access 64 bytes. This is the smallest unit to operate with the memory. The second one is that virtual memory works with 4 kilobyte pages, and they're addressed by 4 kilobytes. Also, we have a very limited cache caches. The first cache is just several kilobytes in size, and since it's organized like a hash table with a sensitivity like a collision chain, so depending on your virtual addresses and physical addresses which you have data placed, you might have even smaller cache size. The second thing is that we have a page table. In modern CPUs, we have a 5-level page table, and in this picture, we have a 4-level page table. And once you have a very large data structure which doesn't fit to TLB, which just can contain about 1,000 pages, which is just 4 megabytes of data. So once you have a very large address space and your application that structure uses a lot of memory, you actually start to miss TLB. And this means that, for example, in this picture, when you need to resolve address of a single green leaf in a binary tree, you need to traverse the whole page table. It means that you traverse the Radix tree and you can access up to 4 different memory locations. So in this sense, when you build a very large data structure, it lives in another data structure. The second thing is about memory ordering. x86-64 provides very strong memory ordering, and this means that we can think that almost no any reordering happen on this architecture, with only one exception, that lots may be reordered with earlier stores. So if we do care about moving lots and stores, we should care about ordering in only one case. We also tried hardware transaction memory Intel TSX for a long time ago, and it provided good performance for very small work set, but we didn't use it for more sophisticated data structure like trees, because the technology rolls back too frequently and performance degrades significantly. So cache-conscious data structure do care about cache line locality, so they do try to reuse each to fully use the cache line. And when you fetch a cache line from the main memory, you try to get as much data from it as possible. We do care about page locality in TLB in this sense, and reuse cache lines. There are several examples of cache-conscious data structures. Unfortunately, they are not log-free, and this is the first trade-off. We can make a good use of cache lines, but when we need to work on concurrency, we need to trade off efficiency in terms of reuse of cache lines and trade it for larger concurrency. For example, we cannot use single instruction multiple data, and so on. Tries hash mapped tries. For this moment, I just reference research about cache conscious parsing trie. It's also not log free, and let's move to our implementations. In our case, we work with inside the cache line. So we start with htry node, which is just an array of integer integers. So we have 16 integer offsets, and we can with each offset we also use one bit, the most significant bit, to mark particular node as the last in hash trie. So we have essentially 31 bits, which provide us 128 gigabytes in RAM addressed with 51-bit offsets. For each index node we use solely one cache line. In this example, we have a string foo. We compute a hash function, and we receive some 8-byte value, and we get the four least significant bits, which reference to nins slots in the array. So with this array, we have at the moment we have a hash table of only 16 items, and referenced by the least significant 4 bits of the key. So we allocate collision chain, and we keep collision chains in buckets. Each bucket is a fixed size of memory, and we have a collision map, which is just a bitmap which we can operate in lock-free manner. It means that we have atomic operations to set bit and read bits atomically. We also reuse one bit in x86-64. We have a bit operations which require either checking of bitmap before issuing instruction, or we need to make sure that at least one bit is set. So in our case, since we have a log-free data structure, we just keep one bit always set. So we have only 63 bits which we can operate for collision map. This is upper bound for collision map, but actually we use much smaller collision chain fixed as just 16 collisions. So we start in a loop. The first thing we descant the tree. In this case, we just have one level tree. In this retrieval of one hash table. Next, we allocate the new bucket, and we write the bucket data to the new bucket. In this case, we write the data by offset 0 because we just created the new bucket and no other data were inserted into the bucket. Next, we have a fully ready block which can be used by other threads. So now we do atomic compare exchange and replace in the hash table just one offset to this bucket. The upper limit for buckets is one system page, 4 kilobytes of data. If we find that the hash table slot is already occupied by some other thread, then we just delete the bucket and retry descending. We need to free the bucket because if somebody already inserted some data into just empty hash table, it means that probably we already have empty bucket and we can insert the data as a collision to already ready bucket. So we free the current bucket and retry the loop. Next, if we since we have a bucket as fixed size as limited by one system page. It only fits to very small data stored in place. The other thing is that we have a bursting tree. It means that the buckets can be reorganized and the data can be moved from one bucket to another. And there are two cases. The first one is when we need to keep large data like web pages, and the second one is when we need to keep pointer stability for small records. So we need to guarantee that once a client code references that data stored in the tree, the pointer is never changed. So in this case, we insert into the bucket only metadata data descriptor, which stores offset to system pages storing the large data or small data. We also use allocator, which is aware about small data allocations like slab caches or large data allocations. So in this sense, we do basically the same thing. We just create the record as a metadata descriptor describing the length, and we do exactly as in previous slide. We firstly build the bucket, we build the large data record, we reference bucket to the large data, and next we link the index with the new bucket. So now we have a bursting problem. So we have our bucket is full, so we already inserted 3 items, and we try to insert the fourth item zoo, and the bucket is full. We need to burst the bucket and spread the data among the different buckets. By the way, in this case we have bad case is that the next 4 bits in all 4 keys are equal to 0. It means that we, when we create a new index node and reference the second 4 bit, they will point to the same slot, and we have a collision again. So this is why we need the top level while loop. It means that we constantly insert new index nodes until we resolve the collision. So the first thing that we do all the insertion code as above, but when the bucket is full, we have a collision and the bucket is full, we do following things. First one, we create the bucket, we copy. First thing is that we create a new bucket, we copy all the data which must be copied by the second 4 bits to the next bucket, and we create a new index node. And the first thing is that we well, in this case, we need to make 2 atomic operations. The first one is to link the current index node with the new index node, and the second one is to change the collision map, the bit map of occupied records in the bucket to the new map, because we can have a concurrent threads running along the index tree, as well as threads traversing inside the bucket node. And this trade-off is that we can observe double records in our tree. In this pseudocode, we firstly prepare buckets, we prepare the index node, we do the cast, so we publish the new index node with the copied bucket, and new bucket and old bucket may reference the same records. And after that, we update the bitmap of occupied records in the old bucket. At this time, concurrent parsing may happen, and this means that some other thread may take out some records and insert the new records. So the bitmap of the current bucket may change. So we need to do compare exchange atomic. However, this compare exchange, we need to read the current value of the bitmap as a current map. And once we read the map, we compute the new records which we didn't copy yet from this bucket, and we redo copying to the new bucket, and we repeat the process. When we observe the same bitmap in current buckets, then we can stop the operation and break the inner loop. That was pseudocode, and this also pseudocode, but with more details. So in this case, we moved records. In this example, we have different success case, and we have a different second level 4 bits, and we have only one index node, and we move it all the records with second 4 bits to a new bucket. And at this moment, concurrent threads may observe the record with second 4 bits as 4 in 2 different buckets. This is our trade-off for current algorithms, and we make sure that deletions never create the bitmaps. So after several retries of copying records, we inside the moving records, we take care about bitmaps in atomic way. After several tries, we see no double records in a new bucket. Reclaiming data is tricky. As I mentioned before, we never clear the index nodes directly. So what we do on freeing some data in a data structure is that we copy the bucket and we set a new link from the index node. So at some point we have 2 buckets, with one with removed data and another without the removed data. And some threads may still be observing the old bucket. So we introduce generations, and generations work in the following way. Every observer, in this case memory readers, in this case inserters or finders, so insert and lookup operations are both considered as readers. They just read the global generation and store it in thread local variable. When an inserter or finder finishes with data structure, it announces that the local generation is infinite. So it means that we do not care about any generation inside the data structure. Removers firstly do the data copying and populating the new index reference to the index node, and after that we need to wait, we need to scan all the threads, what's the last generation they did observe, and we need to make sure that either all the threads observed later generations, or they do not care about data structure generation at all. So in this case, in deleters, we have long loop over all the thread local variables, and we wait when all the readers finish with their data they observe. So this about metadata. Actually, this one of trade-off made in the data structures. We used metadata. Metadata is one more and direction level which introduces additional memory access. So it's not good in perspective from being cache conscious and being constant time. However, this the only way to get the pointer stability and handle large data structure out of index nodes. And also this allows us to keep collision chains and buckets as a fixed size array, which simplifies us log-free operations operating with bit masks and simple arrays. Next, you might think when we consider the first level of the data structure, for example, let's say that we start our work and we have thousands of clients requesting our data structure, and our data structure is empty. And what we have hash tables with only 16 slots, and surely we have a lot of collisions, for example, from competing 100 threads, and this is a good chain that a lot of threads will be bursting the same nodes and so on. That's not a good case. So in this case, we what we do is that we have a constructor for data structure, and you can specify the size of the root entry. And the root entry makes sense to make quite big, like to resolve 8 bits, 12 bits, 16 bits, whatever is a multiplication of 4 bits. The second thing, also trade-off, is that in this case I used hash function to get the key for hash trie. However, we can use plain string as the keys for hash trie, but in this case we can preserve the order, so we can make arrange queries for the data structure, but we get the data structure of unlimited height. And to limit the height, data compressions like hop data structure helps us to reduce the key. So in current version we develop key compression before going to the H-trie to make it more compact. The second thing is that I mentioned that due to using offsets instead of row pointers, each H-trie can address only 128 gigabytes of RAM. This is not so, maybe not sufficient for modern data sets. In this case, we built forest like a set of hash trie, and we share the data among the shards. The good thing is that each trie can be NUMA, not local. So once we have a thread, threads working on a particular NUMA node, working with a particular shard of data, we can distribute ingress requests among the NUMA nodes, different sets of threads working with the different shards of data. This is quite helpful in NUMA nodes. So that's all what I had today. The proof of concept at the moment bit unstable can be found in our blog repository on GitHub. The previous version of H-trie using read-write work for bucket can be found in Tempesta source code. So that's all. So please post your questions. I have one question so far. This attentive did you implement an iterator-based standard C++ container? That why algorithms like cd-stored, ranged for loop, etc. just work? Or was this a custom data structure? Frankly speaking, this is no, we didn't do C++ wrappers. At the moment, this is we mostly develop the data structure to be embedded into the Linux kernel. So this is solely Linux kernel atomics, which is very specific and so on. But we debug and we benchmark the data structure in user space, and we have a C++ wrappers for the data structure. So in short, the data structures is written in plain C, but we use it from C++ testing and benchmarking code.